Good morning, everyone. It's a pleasure to be here, and we have an amazing agenda, and I'm proud to be part of the speaker congregation for this event. So it is my honor and pleasure to be here. And today I'm going to bring forth a topic of my strong interest, which is about AI interpretability as well as fairness. First, very important disclaimer. In this presentation, I'm going to mention a few brands, I'm going to mention a few tools, and it is meant for demonstration only and not meant for comparison or endorsement. Okay, and first we start off with a couple of definitions for the terms. And the few definitions here are protected attributes that includes race, gender, national origin, and so forth. And I think these are very familiar to everybody for employment purposes, for loan application purposes, and so forth. And then the second one is known as bias. And I think this is also very commonly understood by most of the people. So I won't belabor too much on these two. What's obviously missing in this list is a definition for the word fairness, and pretty soon you will see why. For today's talk, I'm going to break it down into three major pillars or three major sections. And the first one's going to be about fairness, and the second one's going to be about reliability when you deploy and when you implement some kind of AI or machine learning solutions, and what are some recommended best practices or architecture from a data as well as a system perspective at a very high level, so that everybody can understand and learn something that's actionable. And then last, I'm going to talk about transparency in such a way that it will help you to understand currently state of the art. How does machine learning and how does AI as a tool can provide some kind of explanation as to how the decisions was made. So let's start off with fairness. We expect from machine learning perspective, from machine learning model designer as well as a stakeholder's perspective, we would like to have the model implemented to be fair to every user, agnostic to their protected attributes, gender, age, and so forth and so forth. However, the problem is the data that was being used to train these models, the data itself are often unfair, meaning that there's always some kind of a bias in there according to how the data is distributed, or sometimes it's intentional, sometimes it's not intentional, and most of the time actually it's not intentional, and that's what makes it very difficult to find out whether or not your training data is balanced. And also the second one is probably the more nefarious one, which is the definition for fairness varies, and each variation has a very strong point. So it totally depends on your perspective or point of reference, and you will see why. This is just an anecdote. I think last year, New York Times published a story that tells about how facial recognition or gender classification algorithms that's currently available in the market are pretty much biased. And it works the best if you're Caucasian and if you're male. Then the error rate is about 1%. And you can see it from this particular figure that the highest error rate in gender misclassification happens if you are female and if you have dark color skin. And the result of this model stems from the fact that the training data is very much imbalanced. A majority of the training data are Caucasian males. So the machine learning algorithm during the training process sort of amplified this bias. And right off the bat, I can think of a couple of ways to correct or guard against this. And one way is, before you deploy the model and make it available for general consumption, at least you want to have some idea at the blind test level with a holdout data in such a way that you can test each of these groups separately. And then the second way to remedy this is to having a balanced data. And there are some tricks, such as generating a synthetic data set or data transformation techniques that can be applied. That's also very commonly used nowadays. But in my opinion, data transformation, data augmentation technique hasn't been done enough. So let's move on to talk about different way of looking at fairness. And one way to look at it is by the group selection rate. Now let's make a case for this particular table. Let it believe that this is a table about college admission acceptance. For group A, 40% of the people in group A usually get selected, and for the group B, 35% selection rate within the group B, and 20% within the group C are selected. And one common way of thinking through fairness actually is adopted by a lot of governmental agency is called 4/5 rule or 80% rule, which means that when you look at the actual result right here and you identify the highest group or the most favored group, in this case happens to be group A, and then you draw an 80% boundary around it, and then you said which other group is within the 80% of the group A's acceptance rate. And if everybody is within the 80%, then we're all good. And if there's a group that falls outside of the 80% of the highest, of the most favorable group, then we have a problem. Then we need to do something about elevating the selection rate for that particular group. In this case, it would be group C that probably needs a lot of help. So if your perspective is to have equal selection process or opportunity within each group, then this is typically how it's done. They look at the highest or the most favorable group, what their selection rates are usually, and then you apply the 80% rule across each of the group. So that's one way to look at it. The bad part about this is it leads to random selection for group C. So all it means is that if I were to remedy this, then the easiest way for me to do is to bump up the quota for group C in such a way that I can make the 80% cut. And the other idea is by feature selection rate, which means that I'm going to select half and half from either group, and I'm going to make up the number like that. So I can select 10 from the male population and 10 from female population and call it quits. But the problem is, as you can see, that some of the group will be highly favored just by the nature that you're born as this, you're born into this group. So is this fairness or not? I don't know. This is in particular contrast to the previous one that you just saw. So this will give the highest favoritism to the minority or to the least favored group, whereas previously that would probably just give the most stringent favoritism towards the minority group. So I guess the truth must be somewhere in between, or not necessarily the truth, but an acceptable fair ground for everybody to be able to move on would be somewhere in between these two extremes. Recently, there comes a new idea, which is fairness by similarity. But this is very difficult to do it right, even though it's very easy to explain. Okay, let's believe that each row of population represents group A, group B, and group C, like you previously saw. And the question is, which one of the group am I more similar with? So statistically, there are ways that you can determine similarity based on different features of the group, as well as the feature that I present forth to the machine learning model, and calculate some kind of a similarity score with respect to each of the three groups. But as to how to do it, whether or not that's fair, whether or not that makes sense for each use cases, That's also a very complicated issue. But nevertheless, the benefit of this approach is it gives you an individual explanation as to which one of the three groups do I look more similar to, and offer some kind of explanation by individual similarity at the individual level. So to summarize what I just mentioned, three different points of perspective for fairness. And the first one is about group, which means that you just look at the ratio within each group for their selection rate. And is the proportion that's being selected same as some kind of a reference population that we have? And if we do, then we call it a quit. So we don't necessarily consider any protected attributes. So the consideration is none. Whereas in the feature fairness, we just want to make it fair for everybody. We can arbitrarily or we can intentionally select 10 from each group, for example, and call it even. But the problem is some group, just because you're naturally born into or aggregated with, you're going to have higher chance than another person that's equally qualified. So that itself presents a problem, but nevertheless, it considers protected attributes to the maximum. And the third one is individual fairness. And this is quite interesting. However, it is very complicated to pull it off and very complicated to justify your calculation for similarity score. So I think it varies as to whether or not or to what degree do you consider protected attributes. Okay, the second topic of the talk is about reliability. And this is more about once you have a machine learning model, once you have an AI model, you want to ensure that performance is consistent this week versus next week as you go on. And you are actively monitoring its performance and how often it misses the mark. And you want to make sure that if there's a drift in a trend, you want to be able to catch it and find a remedy or build a different model or find a different data set to train your model with. So this kind of summarizes the flow or some kind of high-level architecture that we typically propose to our customer, which is it's a cycle from a data perspective. You first train a machine learning model to the best of your liking or to the best of a capability. You deploy it. And now during the deployment process, it's going to start to score on the holdout data or on the new data. But you would not know about the ground truth until maybe several days later or maybe right away. But in any case, someone needs to be there to make the comparison with respect to the ground truth data. And that person has to make the correction for any mistake the machine learning model came up with when you make the actual comparison with the ground truth. And that becomes a newly labeled data. And that data will enable further training for the next iteration of machine learning model to be deployed. So it's a continuous improvement cycle if you look at it. And it does require human in the loop concept in order to pull this off. And typically acquiring truth would take time. For example, it may take you a few days to find out that this person actually is very well qualified for the particular loan based on all the data that you've personally reviewed. So you have to go back and correct it. So that's usually going to take some time in order to pull this off. That's why this cycle cannot be automated as we know it right now. From the data perspective, what we typically see, let's see if the laser pointer, oops. I'm trying to get the laser pointer up, but okay, never mind, just bring my presentation back. Okay, I'm just gonna talk through it. What you see from the top left is a data box. And in some practice, the data has to be split into two parts. You strip out personal or protective attributes such as age, gender, or personal identity, or some kind of a PII. You strip that from the data, but you keep everything else as a feature, and you use that feature data to do the training as well as a holdout before you deploy the machine learning model. And once the model is done, you want to test it before you actually deploy it. So after you test it, you compare that against the protected attribute data that you just separated from. And this would be able to tell you whether or not the results are similar across all groups. So imagine this was the New York Times news article case where you create a gender classification machine learning model and you want to test it, whether or not it's fair for at least all four quadrants of the combination of race and gender. And this is how you would do it. If the results are similar across all four groups, good. You go ahead and deploy the model, and then you continuously monitor and review the result of it. And if it's a no, if the answer is no, like what you saw in the New York Times report, then you probably want to go back and go back to the model training phase and figure out what can you do about data imbalance in that particular case. This is the only slide with mathematical equation in it, but this underlies the importance of capturing some kind of a metrics that kind of makes sense to every stakeholder, from data scientists, engineers, IT professionals, to business or product owners, which is this, and this metric is known as true positive rate. And it is sometimes, it's also known as recall and or sensitivity. So in different literatures, you will come across these different nomenclatures. And what I'm proposing is true positive rate should be measured across at least as many groups as you prefer when it comes to looking at bias. So in a story of a New York Times reporting, if this was done to 4 separate groups at 4 different instances, then it would be pretty clear that the true positive rate for Caucasian male is probably the highest. So this is where one metric or 2 metrics, if you want to look at false positive on the side, then you can also do the same. And also there's a couple of important technical definitions. If true positives are the same across all the groups, then you can claim that this model satisfies equal opportunity criteria. If your model not only satisfies true positive being the same, but also false positive being the same, then you can qualify your machine learning model as compliance to equal odds. So these are just some of the technical jargons or definitions that you may come across in future. Okay, now I'm going to move on to the last topic, which is about transparency or model transparency, or how does the model make a decision and how does a single decision can be explained. So let's start off with this instance. This is a very famous example and very famous data set in open source or Kaggle competition ecosystem, which is a Titanic data set. And we know the story very well. The Titanic sank. Most of the survivors are women, and most of those women are at the higher class of the passenger class, if you compare the first class, second class, and third class. So we know the story very well. And that's going to take, and let's see if we can use some kind of a commercially available tool to find an explanation. So that's what I did. I used a tool called, it's built by H2O as a company, and they have a paid product called Driverless AI. How many of you have heard of it? Good, yeah. I took an opportunity to get a trial license and try it out and see how good it is using a Titanic survival data set, and trying to see if it can help me explain how the chance of Titanic survival can be explained based on all the features in the data. So I pick one particular person that did not survive, and this person happens to be female. And I want to look into it as to why did this person not survive the Titanic sinking. First, I apologize that you probably won't be able to see the red part of it, which is the underneath it. But first of all, at the model perspective, it sort of makes sense to general knowledge, which is if your gender is female and if you stay in the cabin levels of C101 or FE57, those are the higher class cabins. So you're probably wealthy, and you probably stay at the very high level of a passenger level. So that elevates your chance of being saved in a Titanic accident. And some of the negative attributes that would prevent you from being saved would be something like, actually to my surprise, which is number of sibling or number of parents or travel companions that you're with. And if you can see it, those tends to be very high number. And then of course, if you're a male, it decreases your chance by 0.16 as well. But to my surprise, the number of people you travel with actually has a lot to do with it, more than your gender. So how do you interpret this? So let's look at the example that I got, which is this person is a female. Why didn't she survive the sinking? Why didn't she get picked to get on the life raft? Well, it turns out that for this particular person, she is a female, and I don't quite know what parchment means, but her fare is 46.9. So what that means is she bought a very cheap fare, and so some of these are top contributors for her to be safe. However, these values are being offset by the negative attribution, which is that she has five traveling companions, 5 siblings, and she's in passenger class 3, which is the last class, which is probably economy class by today's standard. And then for her embarkation, it's Southampton, and where most of the 3rd class or economy class passenger gets on board. So from socioeconomic status, she's probably on the lower end compared to the rest of the passengers. So this is what machine learning interpretability today, state of the art, is able to tell you, which is provide some kind of a human understandable explanation as to how the decision was made for this particular person. So given the evidence here, I think I interpret it as socioeconomic status is a driver for survival chances in a Titanic incident. And that's how I interpret the data. But without the model, without driverless AI, I won't be able to make that conclusion. I would just be able to say something very generic, which is, well, male probably has less chance being saved than female. But without having a driverless AI to look into it, I won't be able to derive this kind of insight from this particular incident. So in conclusion, model fairness really depends on your perspective. And there's no one clear answer as to what makes a model fair or not. But you have to look at the use case and make your own judgment, make your own justification. And further, it would be pretty hard for a model to conform to all 3. In fact, I think it would be nearly impossible that if all 3 definitions of groupness today can be simultaneously satisfied by a model, and I don't think that's possible mathematically anyway. And also, instead of building an AI model that can perform absolute fairness, perhaps we should scale back a little bit. We should use AI to look at our data and examine whether or not there is bias within our data. And I think we can make much more use of that than expecting AI to be absolutely fair when the data that we present the AI with itself contain a lot of bias that sometimes we know, sometimes we don't even know it. Early progress, such as individual similarity, is pretty novel, it's pretty new, but much more work is needed to be able to make use of it and scale it and be able to deliver the result in a way that makes sense to people. For example, if my algorithm tells you you're more similar to the ones that gets rejected or that for the ones that's being on a wait list, because your score is more closer to this, that doesn't really help you. Right? You just know that there's some kind of score, and that score somehow makes you into the wait list or a reject list. That doesn't really help you that much. So today's state of the art for the model interpretation is really what's known as local interpretable model agnostic explanation, and the acronym is called LIME, and that's what driverless AI uses. And today, it's a viable product, it's available out there. However, it is not free, it is not open sourced. So you have to contact H2O to learn more about it. So for the future work, and these are some of the active research area that you will find in literature as well as in different industries or enterprises, which is decision justification at individual level. That's going to be very important for obvious reason. Suppose a loan gets rejected and that person want to follow up with legal actions, and then this would be something of very useful if you are trying to defend your decision. Data augmentation technique. If we can generate more synthetic data that can make the data set to be more balanced, then in theory, the model will become more balanced or more fair than as if you have imbalanced data set and you expect to do some kind of a post-processing trick to correct it. So I think data augmentation technique have a lot of room to grow, have a lot of applications ahead of it. And it's being very commonly discussed in the open source ecosystem already. And then third would be some kind of a model training framework that can take care of data imbalance problem. Perhaps automating data augmentation technique as part of the training process. So these are the three major work in progress I think you will find across industries. So this concludes my presentation today, and I don't know how much time do we have. Are we doing good? Okay. All right, right on time. It's 10:40 for the break. So if you have any questions, feel free to catch me. So let's just go ahead and resume the break. Thank you.